Everyone, I'm Professor Bob White. It's indeed my pleasure to welcome you to the 69th Conference on Senior Design Presentations here at the Parkview campus of Western Michigan University. This session is hosted by the Department of Industrial and Entrepreneurial Engineering and Engineering Management. We're very pleased that you're able to be with us this morning. We have a number of you here live in person, and we're fortunate the technology allows us to also live stream this to participants around the world. So we're very happy that all of you could be with us and join us in this presentation. We especially want to extend a warm welcome to family and friends that are here with us this morning, fellow students and faculty. We have several faculty that are with us this morning. I'd like to acknowledge the faculty as they've worked very hard to make these things possible. We have Dr. Butt, Dr. Fredericks, Dr. Hoshar, Dr. Burns, Dr. Wells, Matt Cavalli, Dr. Gupta, Tom Schwartz, Dr. Malik. Thank you very much for being with us this morning. Faculty and staff, we're very pleased that you could make it. Another group we want to provide special recognition to when they're able to be with us. It's not always possible. When they are, we're very pleased that they're here. And that is family members. For Donnie Graham, Donnie, we have her parents, Gary and Sally Graham, who are joining us online. Very nice that you're with us. We have extended a warm welcome to you. For Jesse Foster, we have Father Raymond and Mother Joni, and I believe they're here, right there. Very good. Stand up. Let everyone see. Very nice that you could be with us. For David Simon, David, we have Mother Andrea and older brothers Gene and Mike. Well, you're keeping them away online only, right, David? And sister-in-law Lisa and girlfriend Taylor Graham. Very nice that you could be with us as well. These young people came to us several years ago as freshmen, kind of trying to figure out what engineering was and what to do with their lives. And they've worked very hard to put themselves in a position today to present these senior projects. And I think you'll be very impressed with the results. Our second presentation this morning is facility design for a local growing candle company, presented by Jesse Foster, Donnie Graham, and David Simon.
So good morning, everyone. We're presenting our senior design project that we've been working on for the last 2 semesters. So as Dr. White mentioned, our project was facility design for a local growing candle company. We are from the Industrial and Entrepreneurial Engineering Department. Introducing the team here, we have Donnie Graham, myself, Jesse Foster, and David Simon. For the project, we had 2 academic advisors, Dr. Charan Gupta and Dr. Jim Burns. Our company sponsor was Adam McFarland. He is the owner and founder of Kalamazoo Candle Company.
So some company background. Kalamazoo Candle Company was founded in October of 2013. And their 2 best-selling products are jars and tins, as you can see in this image. Over the past 8 years, the products have grown in popularity where they have the products in currently 1,000 different stores throughout the United States. Because our major deals with some entrepreneurship and business aspects, we wanted to look in some of their competition on the west side of Michigan. So if you look at the map, you can see there's 2 stores located. That is their current retail stores in downtown Kalamazoo and in South Haven. The other images on the map are just some of their other local candle competition that are on the west side of the state. So our project followed the DMAE process, which stands for define, measure, analyze, improve, and then control. Now the define phase.
When we first went into KCC, we worked with the owner and tried to establish certain problems that were present in the facility. And we noticed 2 initially. The first were bottlenecks in the current facility, primarily at the cooling and preparation station, as well as the fact that KCC is outgrowing their current facility, anticipating needing to move in 2023. This is further supported by the owner's plans to open future retail stores. So we worked with the owner to derive our project goals and came up with 2 primary goals. The first was to create solutions for the current facility that would allow a daily throughput of 3,500 candles. The second goal was to create a new facility layout for the 2023 facility that could handle a daily throughput of 20,000 candles. This is especially important during their holiday season when they're very busy. Additionally, the owner told us that after this year, they were planning to do 95% production of jars, with 5% of production being tins. So our project objectives are to increase throughput, and this will be achieved by increasing preparation and cooling capacities. We plan to improve the candles per square foot, and we also aim to design a future facility that will tackle these bottlenecks. Next of our projects, one constraint are the unknowns. This is the shape and layout of the future facility internally. And the second is data collection. So the time to collect the cooling data, as this is such a long process, as well as the availability to test different cooling methods. So next, David will walk us through the candle making process.
First thing you have to do to make a candle is you have to melt the wax. This is typically done prior to the shift because it's going to take anywhere from 6 to 20 hours, depending on how much and how fast you want to melt it. Then they go into the first thing they do for the production line, which is preparing jars and tins. This consists of grabbing one of these trays, as you can see. They are 1.66 feet by 1.66 feet. Then you either place your tin or jars on there. After they are placed, they install a wick and a wick holder. And the purpose of the wick holder is that when they are pouring the candle into the jar or tin, the wick doesn't move around. Then they are moved to the pouring of jars and tins. This is done through a single machine where they combine the scent and wax together. Pour times do vary between the jars and tins. However, it is not very much since the sizes for a jar is 10 ounces and the size for a tin, is 6.5 ounces. And typically every 2 trays, they have to refill the fragrance, which is what we call the setup. Then they are moved to the cooling stage, which is done on a flat surface. This is where candles are cured, and this is the longest process of the production. And typically defects do occur in this stage. Then they are pushed to the quality control phase, and there's 2 reasons the candle need to be reworked. The first one would be if there's an air pocket, which you can see in the white candle, or some sort of aesthetic reason, which you can see in the pink candle. And they do this by using an industrial heat gun, and they just simply melt the candle down until they hit the defect, and they let the candle reharden. The last stage of the production line is the labeling and packaging. This is where they apply stickers, they wipe down all the candles and make sure they are clean. They remove any wick holders that are still left, and then they push the candles to the inventory portion of the warehouse. To the measure phase. So this is the initial process that they had when we did our original time studies. It takes about 4.74 minutes to prepare a tray. Then they go over to filling up the actual pour machine, which takes 3 minutes, and next this is the fragrance. Then they pour the actual candles themselves, which takes about 2 minutes per tray. Then if they have to refill the pour machine, it takes about 3 minutes, and that consists of the wax. Then we move to the cooling phase, which is what we had to collect time studies on to understand how long that took. Then they have the quality control, which takes about 4.49 minutes per tray. And then they go to the packaging, which takes 3 minutes for tins and 4 minutes for jars.
So we designed an experiment with 2 main questions in mind. What is the cooling rate? And is there a significant difference between jars and tins? So the experiment consisted of taking the temperature of the candle every 5 minutes. We had 25 samples of jars and 25 samples of tins. So here are some images of the cooling process and the experiment. So what we did was we took a temperature gun and tamped the surface of the candle to record the temperature every 5 minutes. So moving to the analyze phase. So the experiment results. Initially, the ANOVA was explored, and the 2 assumptions of the ANOVA are that the data follows a normal distribution, which we didn't have any concerns over, and then also that the variances are equal. So we had some concerns over the variances appearing equal, so we moved to a Welch's t-test, or Welch's test, which is also a 2-sample t-test. So the response of the experiment was the difference in temperature. The factor was the type of container. Our null hypothesis was that the difference in temperature for tins and the difference in temperature for jars was the same. We did this at the significance level of 0.05. So from the test, we had a p-value of 0.004. Therefore, we rejected the null hypothesis, and we were confident that there was a difference between the cooling and the jars. So for the cooling rate, as I mentioned, we split it into 2, one for tins and one for jars. The R-squared value for tins was 0.9131, and the R-squared value for jars is 0.9284. The R-squared value is an indication of goodness of fit, so 1 being the highest and 0 being the lowest. So we were pretty satisfied with 0.91 and 0.92. So the time to 80 degrees. So from the equation that we derived, we measured the time it would take to reach 80 degrees, which is the ideal temperature for the jars to move to the next stage, or in tins. So that was 150 minutes for tins and 200 minutes for jars.
Once we had our rates established, we then set forth to try and create a model that could show us the throughput of the whole system. So we started off by making this Excel model, which you see here, which allows users to put in different inputs, and that'll impact the time and the throughput at each station. While this was beneficial to allow us to understand the throughput by station, it was a very static model that didn't display the flow throughout the entire workday. So our team decided to move to a more analytical math model.
So our new math model, we took the cooling cycle time, which we derived from the experiment, and then we were able to calculate the cycles per day using that time. So the cycles per day is the operational time divided by the cycle time. That resulted in 2.4 cycles for jars and 3.2 cycles for tins. The spaces available is our design parameter, which is also the buffer space. And then we calculate our tray throughput by the spaces available times the cycles per day. And then the candle throughput is the trays. And since there are 25 candles per tray, you multiply the trays by 25 to get the number of candles throughput for the day. So our equation is spaces available times 25 times the cycles per day gives us our throughput. Now we move to the improve phase of the process.
So for a short-term solution, Kalamazoo Candle Company's goal was 3,500 candles per day. 5% of that for the tins would be 175 candles, which is equal to 7 trays. 95% of their daily throughput would be for jars, would be 3,325 candles, which is equal to 133 trays. The first thing we recommend to deal with the bottlenecks is install a preparation table. The purpose of the preparation table is to limit the bottleneck for the pour station. So the idea is we want the preparation table to be full at 100% capacity, so that when the person who's pouring is done pouring with the tray, instead of waiting on the person who's working at the preparation stage, they can grab a tray from the preparation table. Following that, you can see that we have arrows going to the accumulation conveyor or a cooling station. The implementation of a accumulation conveyor will deal with the current bottleneck for their buffer space. By giving them more room to put poured trays allows them to be able to have a higher throughput of candles produced per day.
The team also conducted some line balance analysis in order to see how many workers and machines would be necessary in order to achieve the desired throughput. So from this analysis, we found that we will need 2 pour machines and 2 people working those machines, 4 at preparation, 2 at package prep, and then 3 at packaging. It also should be noted here that currently KCC is only using 1 of their 2 available wax melters. In order to achieve the desired throughput, they will need to use both. Then took our mathematical model and our cycle time, and were able to determine how much space would be necessary for both jars and tins in order to achieve the desired throughput. From this analysis, we determined that tins would need less space than they currently have, and that jars would need an additional parallel accumulation conveyor, which would be 43 foot long. In addition to this, we will also need the 2 additional preparation workers and 1 additional pour machine and worker.
So here's the production layout. We want to show you it before we show our recommendations. So the first thing you want to note is that the accumulation conveyor is placed on the inside table or the inside of the production line. Then we would like to install 2 preparation tables, and they are going to be placed towards the inside corner of the production line. And something to note is that we actually want to move their pour stations 8 feet from the center of their production line to allow more room for jars and less room for tins. We'll have our 2 pour stations, one located on the inside of the production line, one located on the outside. And then each person, by the way, each different colored person represents a different worker and where they should be located. Moving on from that, we will have the direction of the tins, which will go towards the short side of the production line. After they are poured, they are pushed to the cooling station, and then pushed to the quality control station. There'll be a worker there, and then finally to the packaging station with another worker. Now, if you look at the jars towards the pour station again, after they are poured, they are pushed towards the long side of the production line, go to the cooling station, the quality control station. We'll have a worker designated for that. Then to the packaging station, we'll have also another worker dedicated for that. Once these are packaged, they'll be pushed to the inventory portion of the warehouse. So for a long-term solution, Kalamazoo Candle Company's goal is 20,000 candles. 5% of that would be 1,000 candles for tins and 40 trays. 95% of that would be 19,000 candles for jars and 760 trays. The first thing we recommend is that they purchase this machine through a company called EPAC Machinery. This machine is a remelt station. The benefit of having this is instead of reworking individual candles at a time, they can work a whole tray at a time by pushing just through the conveyor line. In order to get a cost for the station, you request a quote. So they customly built these for your production line, so we weren't able to do this.
So our second recommendation for the new facility is the inventory storage. So we recommend utilizing gravity flow racks for inventory picking. The benefits, automates a first in, first out system using gravity. So they're automatically loaded from the back and then automatically pushed to the front as they're picked from the system. It also allows greater storage space. So it incorporates vertical space and estimated 70% increase in efficiency per our research when we were looking into the gravity flow racks.
Also, once again, conducted line balance analysis for the future facility, and we're able to determine how many workers would be needed per line. It should be noted that in our future facility, the team is planning on implementing 4 lines. So this table that you see here is representative of 1 line, which we anticipate to have a daily throughput of 5,000 candles. So in order to achieve that throughput, we need 2 core machines and people working those machines, 3 at preparation, 3 at package prep, and then 2 at packaging. Once again, utilized our math model in order to determine how long this line should be and derived that each conveyor should be 70 feet.
So utilizing the measurements that we got from the previous slides, we created a recommended production area for the company. That's diagrammed here. Each line, again, will be producing 5,000 candles a shift. One production line has 2 conveyor lines. We split it into 2 conveyor lines to keep a gap between the 2 buffer spaces so as to minimize the heat during the cooling process. There's a total of 6 stations in each conveyor line. And then we created space for up to 8 wax melters, although we anticipate they'll only need to use 7. So just walking through this a little bit. So again, the candles are at the prep table. Then they move to the pour station where they're poured. And then they move to the buffer space, which is 70 feet long, which was from our math model. And then they move to the remelters that David mentioned, and then to the packaging. Additionally, this layout was created to accommodate personnel space requirements for the workstations. So systematic layout planning. Workers and departments. The total area of our new facility, the total working area, is 19,760 square feet. The hallway space accounts for 240 square feet, and the total employees are 57 workers. This accounts for 40 in production that we got as required to get the throughput that we wanted. And then additionally, we estimated their increase in total employees as they continue to grow.
So we understood our departments and the sizes of them. We then were able to construct a relationship diagram, which you can see here. And in this diagram, a rank of A means that departments should be close together, all the way through a rank of X, which means that they should be kept separate. After we ranked the diagram, we then went on to score it. So anything that had a rank of A now has a value of 10, all the way down through X, which has a value of 0. We then took this matrix and implemented it into a software called VIP, which spits out different layouts and different possibilities for your facility. So VIP generated 3 layouts that we liked initially, which were seed 4, seed 6, and seed 17, which we then modified to look more like an actual facility and be a bit more realistic. Our team then chose the modified seed 4 and designed our actual layout in Excel. So as you can see here, we have our production area, which will flow into shipping and inventory with raw material storage nearby. And then we also have the non-production areas with a break room and conference room available in the new facility.
So talking about the results from our project. So we set out with the goal to increase our current throughput. We moved from the initial production layout to our recommended production layout. This has an anticipated increase of candles per day of 1,500, moving from 2,000 candles per day to 3,500 candles per day. Additionally, we set out with the goal of creating a new facility. So we moved from the initial production layout to the one that we generated to accommodate their future throughput of 20,000 candles. So in terms of candles per square foot, the initial layout had 1.11 candles per square foot. We anticipate an increase of increase to 2.37 candles per square foot. So if we look at workers per 1,000 candles, that is the workers required to produce 1,000 candles. In the current state, it's 5.1. The short-term solution, which is the top solution there, is 3.7. And then in our long-term solution, we anticipate that goes down to 2 workers required for every 1,000 candles. So we'd like to thank our academic advisors, Dr. Jim Burns and Dr. Gupta. And we'd also like to thank our company sponsor, Adam McFarland, for without all of them, this project wouldn't have been possible. So we'd like to give a big thanks to all of them. And then also we were curious about any questions.
Again, any questions from the in-person or the online groups?
So the new bottleneck we anticipate to be the pouring machine. So we anticipate continuous pouring. So the throughput was designed to accommodate for the rate at which the pour can pour.
Absolutely. How is that incorporated in your data?
Yeah, so like you said, the candles inside do cool faster. So we went for that time for how long it takes to cool and go to the rework station. So the numbers you have right here were actually based off the inside candles, not the outside ones.
Yeah, so the longest cooling time is what we went with because we assumed that they'd be processed at the same time.
So as a
That's that option with our sponsor, but it was a little bit outside of our scope for this project.
Yeah, based on, you really got long-term.
I believe that was around 2025.
Okay.
Was anticipating reaching.
It's pretty serious growth.
Yeah.
From Neil, in the lines you have set up, will there be space for people to do repairs as needed?
Yeah, so by having it being 70 feet long, we kind of figured that if there's any processes that need to be fixed or anything like that, we'll be able to have space for it just because how long we made it and also how much space we gave in between each production line.
Also, if he's talking about the machines themselves, the pourers are actually on wheels so they can move around, so they could be moved out of the production to fix them if required.
Additionally, to add on to that, we left generous aisleways between the production lines to allow for easy movement between.
There's one faculty member that we need